it burns, it combusts with some other fuel, like hydrogen and oxygen, for example. The temperature goes up, the pressure goes up, and therefore the volume increases and it gets shot out the back. All right, so that's kind of how it starts moving in the first place. That therefore means there's a force on the fuel this way, which means there's a force on the rocket in the opposite direction. So if they ask you this in exam, perfectly acceptable answer. We can also think of it in terms of momentum as well. Okay. So when it's stationary, what's the momentum? Well, momentum is mass times velocity. So if it's stationary, momentum equals 0. Momentum is p. When it's moving, then what's happening? Well, the little individual fuel particles are moving with a really high velocity. So what must, actually I'm just going to put mv, I'm going to put minus momentum. So the rocket has positive momentum. So overall, momentum still equals 0. Right, why is that? Because momentum is always conserved. Right, that is a law of physics, a fundamental law of physics, which is true. It's not immediately obvious why it's true, but it is something that is true in physics. Every single experiment we've done shows it to be true. We can prove it mathematically as well, but it's a little bit beyond A level, so we're not going to do that. So in this example here, it should be fairly obvious. Which one is going to be going faster, a fuel particle or the rocket, which is going to have the highest velocity, and also why? If you could just type your answer. Oh, thank you, Naveed, for that. Tell him to turn it off and on again. That usually works. And tell him I'm also recording the lesson as well. You can also tell him that he can go on to the PowerPoint on the website and then still do work. Right, yeah, so please type in the chat, which is going to be going faster, the fuel or the rocket, and why in one sentence. Should be a fairly easy question for you to answer. Right, so if you just type it in the chat, rocket or fuel, which is going to go faster? And then one short sentence, why? So whenever you're ready, type it in the chat. So it's a 50-50 guess. So you should all be able to put in either fuel or rocket, even if you're not sure. All right, well done, Amirali. Amirali is correct. right? Hopefully that should be fairly obvious, even without doing the maths. Right, the thing with the least mass is going to go faster. So you're basically right, Sammy, but you should really use the word mass instead of lighter and smaller. Lighter kind of implies weight, and smaller doesn't matter as mass. So how do we define the conservation of momentum? If they ask you to define it, we would say the total momentum of a system, I'll come back to system in a second, remains constant provided that no external forces act on the system. So why do we say system, and what do we mean by system? We just mean all the things, basically. So hopefully it should be fairly obvious. The system here would be everything, the fuel and the rocket. If we only look at the rocket, clearly this isn't true because it has zero momentum, it has positive momentum. That's clearly not true, but we need to look at the whole system. Obviously, if I come along and I just poke this with my hand, it's going to change its momentum because it's an external force. So again, if I come along and poke it with my hand and look at just the fuel and the rocket, momentum will not be conserved. But in this case, then the system would be the fuel, the rocket, and my hand pushing it. So the system might change, but it's important that we realize exactly what we mean by the system. So this is definitely something to learn. So we're going to look at a couple of different examples of conservation of momentum now. And we're going to look at different types of collisions. But there is one other thing we need to define before we can look at momentum, and it'll become a bit clearer later on. So we've basically got two types of collision. We've got a type of collision where the object might do this. Or we've got a type of collision where the object might do this. All right, you might know what these are called. I think we've sort of mentioned these things before. But we've got two types. We've got an elastic collision. And what's the opposite? You can probably guess if you don't know. Inelastic collision. So what's the defining feature? In an elastic collision, kinetic energy is conserved. And in inelastic collision, again, you can probably guess, kinetic energy is not conserved. So here, if it has a velocity of 10 meters per second, it will be going back at minus 10 meters per second. Here, if it has a velocity of 10, it then has a velocity of 0. Why is this not the case, right? Why would kinetic energy not be conserved? I mean, it should be fairly obvious from the picture, right? There's a couple of reasons why. It could be the object is deformed and squashed, or it could be due to heating. So it could be that we've had a load of energy transferred into a different form, such as heat, and therefore it hasn't gone back into the kinetic energy. So a bouncy ball will do this, an elastic band will do this, a piece of plasticine would do this. Right? A car crash is more likely to be this because cars are designed to squash as a safety measure. So why does this matter for conservation of momentum? Well, because we have different types of collisions. Right, we could have a type of collision where we've got a car and another car. This is before. And then after, what could happen is they could end up squashed together like this. All right, they might still be moving, but they're squashed together. So this would be an example of inelastic collisions where kinetic energy is not conserved. How would you show that? We'd obviously work out the total kinetic energy before, total kinetic energy after. There'd obviously be a difference. In terms of working out what the speed is, what do we need to do? We need to realize that momentum is conserved. So the momentum before equals the momentum after. So we need to now give our objects some labels. So you can give your labels anything you want. I'm just going to call them 1, 2, and 3. So the momentum before is going to be m1 v1 plus m2 v2. The momentum after, well, what has happened? They've joined together. So what's the mass? The mass is the mass of the first one plus the mass of the second one, and then it's going to be multiplied by the new velocity. So it could be v nu or v3. And then it's a case of plugging in your numbers, basically. So if you did triple science, you would have done things like this. But I do realise that a lot of you may not have done triple science, and a lot of you may not have even studied mechanics very well, because it may have been the last thing you did last year, which is not a problem at all. Are there any questions before I move on? Okay, so another possible collision could be something like this. So let's do before. So again, we'll say m1 v1, m2 v2. Actually, let's make that one go in the other direction. And go left. And then after, and then afterwards, maybe they're going in opposite directions. So here, again, what do? We say that momentum before equals momentum after. So m1 v1 plus m2 v2 equals m1 v3 plus m2 v4. So here they've undergone some kind of elastic collision, which means the masses have not added together. And again, basically just plugging in numbers. You generally need to know more information for this because there's obviously an extra variable, an extra speed, and an extra velocity you need to know. What's really important in these types of questions, particularly in this one, it is important in this one as well, but it's probably not quite as important. These ones that can be more complicated. What you need to do is you need to define a positive direction. So for example, right equals positive and left equals negative, because then here we've actually got m1 v1 and we've actually got minus m2 v2 here because the momentum's in the other direction. This would be minus m1 v3 and this will be plus m2 v4, okay, because our directions will tell us whether things are going left or right. All right, you've got to be really careful, otherwise it just won't make sense. Are there any questions? Right, so we've got here a nice animation. And you can see this in practice. Well, this is more like the rocket one. This isn't a collision. So we chop this in half. The gas inside or the liquid inside expands. As it expands, it exerts a force on the two halves. One goes one way, the other one goes the other way. And you can see that one goes faster, one goes slower, which means that probably the left-hand side has a lower mass and the right-hand side probably has a higher mass. And you can see that before it's stationary, so before the momentum is zero, afterwards we've got positive momentum, negative momentum. So again, afterwards, the momentum is also conserved. So this here, just like the rocket, is an example of an explosion. And in physics, explosion generally has a quite a specific meaning. Hi, Razan. Razan, I have been filming this, so you can catch up in a minute. So if you ever see explosion mentioned, it's any situation where there is zero momentum at the start. So here, for example, if this was a balloon popping, and these are the little bits of the balloon going in opposite directions, at the start, zero momentum. At the end, momentum in many directions. I think the slow-mo guys, if you've ever seen them, they do some nice videos of balloons filled with paint popping that are worth watching. They're quite pretty, actually. And you can see this obviously in action. You can see the paint go in all different directions because momentum has to be conserved. Other examples of this, if you ever go ice skating or if you sit on some wheelie chairs and you push the person on the wheelie chair opposite you, or maybe on a skateboard, what's going to happen? You're both going to end up going in opposite directions, again, because momentum is conserved. Again, this technically would be an example of an explosion, right? Not your traditional everyday explosion, but a physics explosion. All right, there's one more area I want to look at, then I'm going to set you off on some questions. And I just want to prepare you for the fact that they could, if they're being mean, give you a two-dimensional situation. So something like this. So two things collide, and then they go off in different directions, and we're now working in two dimensions. So you might already have an idea how you solve this. It's a little bit tedious, but it's not hard. So again, what do we need to say? We need to say always momentum is conserved. But now we're working in two dimensions, so we need to consider two different things. We need to look in the x direction, and separately we need to look in the y direction, just like we do for projectiles. So in the x direction, what is the momentum before? It's going to equal VA times by the mass of A plus B, which in this case actually is 0. What's the momentum after going to be? Well, it's going to be VA, I'll put VA2, although I realize this might get confusing, but we want it in the x direction. So we only want this component here. So what's this component? VA cos theta A. And then obviously times by its mass, plus same for B. We want this bit here, which is going to be VB cos theta A. So plus VB, probably should say 2 actually, because this is afterwards. Okay, so now we've got two equations, right, which are going to be equal to each other. What about in the y direction? So in this specific example, is there any y motion before? No, it's actually 0. So afterwards, what have we got? We've got the y direction of v. Again, I should probably put 2. So we've got v a2 sine theta A times by the mass of A, and that's got to be equal to the momentum of B times by the mass of B, because there's 0 before, so whatever the momentum up, it must equal the momentum down. So now you've got equations which might be really easy to solve depending on what information you've been given, or you might have to do some, slightly mean substitution in. I'm not going to do a specific example at the moment. I think there might be a worked one later on. But certainly if you finish everything, I'll give you some harder questions, and I'll give you some harder ones of this if you want it. But all you need to remember is it's really simple. It's like projectiles. You split it up into x and y directions. You treat each separately. You do the conservation momentum for the x direction. You then do it for the y direction, and then you can solve whatever you need to solve. Right, are there any questions about this? I am going to take a photo of both these notes and put them up just in case you came late or you missed something. And then as soon as the recording has uploaded, I will put the link on the classroom. What I'd like you to do, please, is open the lesson. I'd like you to work through the 2 videos of worked examples. The first video is quite standard problems. The second one is a classic exam question, and it's a bit more challenging. I do make a very stupid mistake in the second video. So if you think something is wrong, it is wrong, and then I only realise at the end and I correct it. Once you've done that, there is a worksheet with some questions on for you to finish, also for you to work through. So please make a start of that, and if you've got any questions, obviously do ask them.